Welcome to the first DBA Office Hours for 2020. For those who have never been on one, my name's Connor McDonald, and to get in touch with me is very, very easy. That's my Twitter handle at the top there, Connor_MC_D. And rather than bore you with 37,000 links to 37 kinds down, let me try that again. Rather than bore you with 37,000 links to other social medias, you can get it all on Linktree/Connor, which has Facebook, Instagram, blog, etc., etc. So love to see you all there. Hopefully you can hear me and see me, and you're not getting the hideous feedback that I was getting. I need to warn you, it's been like just below 40 degrees in Perth all week. So literally, you can rest assured by the end of this session, I will be dripping in sweat because it has been very warm and my house is very warm as well. So what do we got in the chat already? Is there anyone with his micro not muted? No, I think it might have been me. So it might have been me originally, Patrick. So hopefully that should all be good now. As I always say, do not adjust your set. Whenever you're seeing the slides, the content will appear shifted down toward the left. That's simply because when we turn this into a YouTube video later on, we can align the speaker, namely myself, with the YouTube content as well, so it all sits in nicely. So no need to panic there. As I normally do at the start of each office hours, I talk about a few bits and pieces of things coming up, things that have happened, etc. Hopefully to keep you in the loop as to what I'm doing and what the rest of the team is doing. So let's talk about that briefly. I put this slide in there for myself. Funny story for you, last month we did office hours and I forgot to record the entire session. So if you've seen the YouTube video, that was done the day after when I redid the entire office hours session to a blank screen, just trying to simulate talking to an audience. So that was a little bit of fun. So let me just check. Yes, I am recording. Save myself some time. You'll notice now we have a new webinar format. It used to be the case if you've been on office hours sessions that you would join a meeting and anyone on the meeting could actually see everyone else on the meeting, etc. We had a bit of feedback saying that sometimes that gets a bit complicated. People inadvertently turn their video on or their microphone on, etc. So we've converted to the new Zoom webinar format. I want to stress, don't panic. Yes, you would have been asked for a name and an email address to get on. That's simply just such that we can identify you by name on the chat. Your email address is not logged anywhere. We're not going to spam you, etc. In fact, you can feel free to type in anonymous@anonymous.com. All we really need is your first name or your name, such that if you put something on the chat, we can refer to you. So don't panic. That's the new webinar format. Hopefully it'll run a bit more smoothly, assuming I can keep my damn phone turned off. What's coming up for me? Well, next week actually, in fact just 1 week, a couple of days after next week, I'll be heading over to the Italian user group conference. Can't wait for that. That'll be Milan and Rome. So hopefully if you're in Europe and you're somewhere in Italy, please come along and say hello. Straight after that, it's off to Israel for the Israel user group. This is my first time. Was there last year. Had a fantastic time. Lovely hosts, brilliant attendees, fantastic content. So if you're in Israel and on the call, please come along and say hello as well. Love to see you. That'll be literally straight out from Italy onto Israel. And I've got Apex World coming up in April. Interesting, I was on what we call an all hands meeting, an internal meeting for all the database group inside Oracle last week. Obviously I can't share exactly what was said, but one of the things that one of the very senior executives spent a good deal of time on was the amazing uptake and popularity of Apex in the community. And so if you're a DBA on this call or a developer, I can't stress enough, get your hands dirty with Apex if you haven't in the past. Oracle has decided, and I think with great reason, to decide that, hey, it's a really strategic product and incredibly powerful. One of the team members on Stephen Foyer's team, Dan McGowan and myself, we're currently building a little Apex prototype to see how it runs against a multi-billion row data warehouse. And so far, things are looking pretty awesome. Now, it might be daytime for you, but I literally took this 5 minutes before the call. That's why the slides are a little bit shuffled around. I thought, oh, what a great day. It's been so hot in Perth. That is literally the view out my backyard onto the park. That was the sunset. I can still see it not more than 10 minutes ago. So beautiful day in Perth. If you're in the wintertime, you have my sympathies. But enough jibber jabber. Let's get on to what we want to talk about. I promised on Twitter 10 minutes ago that we would finish before the hour because last month I went way over, and I feel bad when I do that. So we're only going to cover 4 things, and we'll try to get them done in the hour, which is the dreaded Aura 257. I don't have any prizes to give away virtually, but if you know what a 257 is off the top of your hat, then yeah, feel free to slam it in the chat line, but we will talk about it. Issues with the result cache, rebuilding indexes, and slow queries after maintenance. These are all questions that have come in from you, the community, to talk about on the DBA Office Hours. There were a couple of others, but they were sort of one-line answers, so I'll simply convert them into Ask Tom questions and publish them as per normal. So if you have asked a question for DBA Office Hours and you don't see it here, rest assured we are going to throw an answer out on Ask Tom for you. Let's get straight into Aura 257. No one's put in the chat what Aura 257 is. That's probably a good sign. That probably means you're a good DBA if you're a DBA on the call, because ideally you should never get this. What is Aura 257? Well, here's the question that came in. Is it okay to shut the database down when I get an Aura 257 and then restart it after sorting out the space issue? This is the question that came in, and maybe that might give you a hint as to what Aura 257 is. Aura 257 is the bane of us as DBAs because it's this. When an Aura 257 occurs, what it means is you can no longer archive your redo logs. And pretty much from that point onwards, your database is dead in the water. You try to delete and it says, I'm sorry, the archiver is in error. Connect internal only until freed. That is a somewhat obsolete message for those of us that are a bit long in the tooth like myself. Back in the day when you wanted to connect a sysdba to the database, you fired up a product called SVR MGRL, Server Manager Line Mode. And instead of doing connect/sysdba, you would do connect internal. You were connecting to the internal parts of the database owned by sys. So that's what the error message refers to, the fact that the archiver can no longer archive a redo log. And you're pretty much stuffed at this point because you can't do any DML. You pretty much can't do anything that would try get the database to move forward, because anything that moves forward generates redo typically, and you can't generate redo because your archives are full. Even trying to connect will give you an Aura 257 archiver error. The only thing you can pretty much do is connect/sysdba. And so a common question is, can I shut the database down to sort this out? I've got a disk full. How do I solve this problem? Can I just shut the database down, jump onto the OS, remove some files, and I'm good to go? So I want to talk about this common technique first, the thing of shutting the database down such that you can do something. And the answer to that is no. Do not shut your database down to solve an archiver internal error. And I say sort of, there is no risk, there's no problem with doing so. You can quite happily shut your database down at any time. It's always going to come back up again. It's very, very resilient, the Oracle database. But the reason I say no, you shouldn't ever shut your database down to solve an archiver internal error is for 2 reasons. The first reason is unrelated to archiving at all. The first reason is just don't shut down. It's a bad idea. And we have discussed this on a previous Office Hours session. So just to recap extremely quickly, one of the reasons you pay the big bucks for quality software like Oracle is, well, we have a very sophisticated thing called a buffer cache, which stores information from disk in memory such that you can access it faster. Shut the database down, you throw all that value away, and it has to repopulate next time you start. It costs you in terms of performance. There's also a thing called the library cache, all the parsed representations of how to run SQLs, optimizer plans, etc. Throw all that away when you shut down. Now you've got to parse everything again when you start up. Once again, more expensive use of resource, slower performance. You've got an in-memory store perhaps. That's even more critical because unless you're using some of the fast start in-memory algorithms that came in 12.2, what it means is when you restart, your CPU is going to work very, very hard to repopulate that in-memory store because it has compressed data in it. And more importantly, you're taking an outage. You're taking the database away from people. You could perhaps argue that if you've got an Aura 257, you've already taken the database away from people. But don't forget, people on the machine who currently are just running queries will so far be blissfully unaware that you've actually got a critical problem here. So if you don't stop the database, hopefully they can continue doing queries by and large. Anyone trying to do DML is going to be stuck, but that's hopefully why we're trying to avoid this problem in the first place. But if you want to learn more about why I think you should never shut your database down unless you absolutely have to, that link there, bit.ly no more shut, is a link to the office hours session we did back in the past where I spoke about at length as to why you don't want to shut your database down, period, let alone to solve ARA 257. The second one is shutting your database down is often what I call the road to ruin, where you're being sneaky. Now, what do I mean by being sneaky is you're not talking to your database. You're not keeping your database informed. Now, let me explain this better with a picture. This is what your database looks like. Everyone's database looks like this. It has a series of files and you have some database software running, and the whole thing obviously is sitting on a server which has an OS. Now, excuse my terrible joke here, there you have some archived redo logs. Yeah, no, terrible. Archived redo logs obviously sit on the operating system file systems, or they could sit inside ASM, but ultimately they're sitting on physical disk somewhere attached to that server, either directly or via network. But two things are aware of those archived redo logs, and in particular the fact that you've run out of space. The operating system is obviously aware of space consumed. If those archive logs are sitting on a file system, the operating system is aware of how much space they're consuming. But also the database is aware, and this is where people often forget. The database also keeps track of the archive logs it's got, how much space is being used, etc. When I say don't be sneaky, if you just jump out to the OS layer because you've shut the database down to try solve a space issue, what you're really doing is liaising solely with the OS and not keeping the database informed. And as I said, this is how the OS represents its knowledge of a full archiver issue. You might pick a particular file system. I've got, this is a bit of fiction here, but I've just typed it in what a df command typically looks like. You go to a particular volume, you can see it's 400 gigs of size, it's 400 gig utilized, 100% full, and it just so happens to be mounted on /db/archives. That's often a telltale sign that, yep, I'm out of space for archives. But the database knows about archives as well. And just like df is a critical tool for using at the OS layer to see what something is full, the alert log is critical for knowing what's going on inside your database. And if you're using the flash recovery area, then you'll start seeing these kind of things in your alert log. By default, once the database archive area or the recovery file destination area gets to more than 85% full, it's going to start letting you know. It's going to start spitting error messages like this into the alert log saying, you're starting to run a little bit close to the wire here. You need to solve things out. So both the OS and the database have feelers, connections, information. They're liaising with the archive log subsystem to know what things are full. If you just jump onto the OS because you shut your database down and start removing archive logs, yes, you've freed up space in your archive file system perhaps, but the database will be blissfully unaware of this. And in fact, it will continue to think that the archive space is full if you're using a recovery area like this. It's not good enough just to go pillaging through the file system to remove archive logs. And as I've said in previous office hours session, that's just a horrific idea anyway, to have your database be unaware of missing archive logs, because that's going to cause all sorts of grief if you ever have to do a database recovery. So my point is here is keep the database informed, and the best way to do it is simply not to shut the database down. Do all these fixing operations through the database interface, and then you know that the OS will take care of itself and the database will know what cleanup activities you've done to free up space. So what are the things you can do to fix ARA 257 if the database is not being taken down and you're only doing it through the database interface? The first one is you can delete obsolete backups. You can go into Recovery Manager and simply say delete any backups that are obsolete. That will clear up and free up space that are used by backups, which all sits in that same chunk of space, which is the recovery destination. If you don't want to, if you simply say, I've got an ARA 257, people are screaming at me, the phones are running off the hook, you just need to solve this problem quickly. The quickest and easiest way is simply to increase the recovery file desk size. If it's currently listed to 400 gigs, even just bumping it up to 410 is going to let you archive a few logs while you now go do things like delete obsolete backups, perhaps move things around, etc. So that's your quickest and dirtiest, or I shouldn't say dirtiest, that's your quickest option to simply get people up and running again. The other one is temporarily change the archive log destination. What you can choose to do, did I put it here? Yeah, sorry, let me go back one. You can temporarily change the archive destination. If you're not using the DB file recovery area, the flash recovery area, and you've allocated your log archive destination to a particular file system, just flick it somewhere else. Leave that one full, flick it somewhere else, let some archives go there while you solve the problem more permanently in the background. Once again, it's about getting people up and running again. A slight variation of that is if you are using the flash recovery area, then what you can actually do on that parameter is say the archive area points to the DB recover file desk location. You can also then append to it say alternate equals and then another destination set in log dec archive desk 2. And once again, it's like a piggyback system. We use the recovery file destination first. If we can't, then we have an alternate location. Once again, it's a way of temporarily pushing archives somewhere else so people can stay active and then solving the problem by, for example, increasing recovery file destination size, deleting obsolete backups, backing up your archive logs so you can now delete them because you now have a backup, etc. One thing I should stress is most of the log archive desk parameters have a facility to work out when to go back and see if a problem has been resolved. And that's the reopen parameter. It defaults to 5 minutes. So if you get ORA 257 and you rush around and you fix a problem with any of these things, deleting obsolete backups, etc., it's probably going to be somewhere between 1 and 5 minutes before actual operations will resume, because it'll be between 1 and 4 minutes for that 5 minutes, that 300 seconds, before the database goes, yep, let's go see if the DBA has fixed things up. Generally, in a lot of databases I've ever worked on, the first thing I do when it comes to setting up my archive logs is changing reopen to say 60 seconds, such that every 60 seconds I know I'm going to be a little check to actually do what's going on. I should note that you can actually forcibly put that in a parameter. So if you've fixed a problem, you can simply say alter system set log archive desk 1 equals existing setting space reopen. And that will just do a reopen right there and then to make sure that you're not going to wait that 5 minutes. But for me, I just like having it at 60 seconds such that I'm always know that every minute I'm going to check in case I've had a problem and then it's been resolved. So at worst case, I'm going to be waiting around for 60 seconds or my own latency in terms of fixing the problem. But overlying here, notice that none of these things are talking about heading out to the operating system. It's a common thing that I see. People, I'll jump out to the OS, I'll compress some archive logs, I'll move some around, I'll delete them, etc. All those things then require remedial action in the database for the database to be kept informed. I would much rather you go through the database interface such that everything is always kept in sync. Your RMAN catalogs, your control files, and it'll take care of the operating system files itself. Hopefully that makes sense. That's number one. How are we going? 8:19. Yeah, we are going to get done before 9 o'clock today, my PM. Got it. Let's talk about result cache. Even with result cache memory allocated, sometimes you run a query and it doesn't seem to use the result cache. And you've done all the right things. You said, I've got a result cache size set at the database level, so I've allocated some memory in my shared pool for the result cache. I'm using the result cache hint, and yet things are never cached. What is going wrong? And I thought I'd present a very, very common kind of scenario, a common error that happens when we're trying to use result caching and we get burned by it not being used. Someone's saying, I'm trying to get this current month's sales. And the overriding thing, the most common reason why a result cache will not be used is our mantra, a database mantra, which is correctness trumps speed. And that is, like almost everything inside the Oracle database, our fundamental goal is always to give you correct results over every other thing. And a good example of that is, for example, if you do a count star from an indexed table. You know, people say, how come I can't use the index? Well, if the column is defined as nullable, the index possibly might not contain all the entries, and therefore we would refuse to use the index. By default, Oracle will always choose correctness over speed unless you explicitly say it's okay to not do so. It's like query rewrite integrity for materialized views. By default, we have to guarantee the materialized view rewrite will give the same results unless you explicitly say, I'm going to relax those settings by setting query rewrite integrity. So by default, correctness over speed. And that's why sometimes we won't use result cache if we have a questionable in terms of correctness. So let's look at some examples of that. Let's do a new share. Okay, hopefully everyone can see that's a SQL Plus window. Hopefully the font is large enough. Now, what do they call it? RC, I think. So I'm going to create some sales here. The scenario I'm going to talk about is doing this month's sales. Let's create some sales. And unrelated to result cache, I thought I'd show you a little quick tip here. When you're trying to populate lots and lots of data for test data, I might be doing a lot of stuff. For example, I want some random numbers. This table here is going to have 10 million rows in it, this sample data I'm creating here, and I'll show the data shortly. Calling dbms random to get random data 10 million times is incredibly CPU expensive. dbms random is an expensive function to run. And as long as things are roughly random, maybe that's all I need. So if you ever had to populate large volumes of data and there are expensive functions in there, sometimes you can cheat. What I've done here is I've said, I'm going to go get 10,000 random amounts for my sales, but only 10,000, not 10 million. But I'm going to materialize that. So now I've run the dbms random function only 10,000 times. That's going to run fairly quickly. Then I'm going to use that amounts table as an input to populate this table called sales with 10 million rows. How do I take 10,000 rows and multiply it out to 10 million? I simply repeat it 1,000 times. So this way I get 10 million rows, but I've only called dbms random 10,000 times. It's a cute little trick to limit the overhead of expensive calls. Doesn't matter if it's dbms random or square root or anything which is going to be CPU intensive. If you can get away with running it less, things will run faster. But that's outside the discussion. Just a little tip there for populating tables with a lot of rows. So this table called sales has 10 million rows. Let's see what it costs us to run a query. So this one, I'm running select some amount from sales where customer greater than 0. It took around about 0.8 seconds. If I run it with result cache, it also takes about 0.8 seconds because we know that the first time you run a query with result cache, it has to populate the result cache. So this one has actually gone and run through the whole set of data. We can see here by looking at autotrace that it actually did, where are we? 35,800 physical reads. So it went out and read the whole table, and with those results now, it has primed the result cache. So the second time I run it with the result cache, instantaneous. Now, 0.8 of a second wasn't a big deal anyway, but we can see here the key thing is my physical reads has dropped to 0. So instead of 35,000 physical reads, now it's 0 because this query, the first execution primed the result cache, the second execution took advantage of the result cache. So it's result caching in a nutshell. It's pretty cool. Let's now do what the requirement was in our little scenario here, going and getting this month's sales. Now, how do I get this month's? I can take sysdate and truncate it down to the start of the month. That simply says the 1st of January. And then I can take the same thing, truncate sysdate down to the 1st of January, and then add 1 month to it. That gets me to the 1st of February, and I'm getting everything less than that. So inclusive for January and exclusive for the 1st of February. And I run that. It takes, once again, about 0.8 of a second. I didn't want to make this too large for you because it would bog down the call. 35,000 physical reads as we expect because that's the size of the table. So I run that, I run it again, and it's still 35,000. I was just seeing what the time was here. It's about the same time. So I don't like 0.8 of a second. Obviously, I'm a very fussy user here. So I'm going to put a result cache on it. This first execution will hopefully prime the result cache, so it takes 35,000 IOs as before. And the second execution, here's where things get a bit disappointing. You can see my first query here should have primed the result cache. I should have run physical reads and then primed the result cache. The second one didn't prime the result cache. That's a bummer because I'm still at 35,000 physical reads. If it wasn't 0.8 of a second, but 80 seconds or 8,000 seconds, this would be a big drama. The question is, why? Well, as I said, correctness trumps speed. We know, as people who architected this code, that these two things are, from our perspective, constants for the sake of all of January. From the 7th of January up to the 31st of January, these two things are going to return the exactly same figure. But the database doesn't know that. It simply sees a reference to sysdate and knows that every time you run this query, sysdate has inched that little bit further on. It doesn't know that we're only interested in month boundaries. It simply says sysdate has said it's changed. I can't cache that result. How do we solve this? It's actually relatively easy. If you know, as a developer or DBA, that certain elements that are derived from a dynamic function such as sysdate, systimestamp, etc., are for the purposes of your query, in fact, static, then you can simply tell the database that. So what I'll do is I'll simply store my value of sysdate, which is today, in this variable called today, just the string variation of it. Now I can rewrite my query to reference this variable. This is now static from the sake of the point of view of the database. It's unchanging. The first execution, as I said, needs to prime the result cache, so we simply do our 35,000 reads. But the second execution, hey presto, now we're getting some real value. So the most common causes I see of result cache not being used are you've written a query that you can't guarantee to the database wouldn't change on multiple executions. Sysdate, systimestamp, maybe you've got a sequence.next val in there. There's a whole range of things that you might know are unchanged for the purposes of the query or for the results of the query, but the database does not. And correctness is always chosen over speed. Unlike things like materialized view rewrites, where you can nominate the integrity of the results with result cache, if the database doesn't like it, you're going to be in trouble. You can actually cheat a bit more with the PL SQL result cache, but for SQL, the database decides whether it actually going to obey the result cache hint. One of the good things is we've improved this with each iteration of Oracle. When result cache first came out, any reference to a syscontext variable would actually immediately disable the result cache. It couldn't be used. And I was actually preparing this as an example tonight of, look, here's another example where it can't be used, but I was pleasantly surprised. I've set the module to the value of 0, such that I can reference it in the syscontext module function. So this is going to come out as the string of 0, which I'll convert to a number. So I can run that. The first time I run it, I prime the result cache. I was going to say when I was producing this demo, because there's syscontext in there, the second run will also not use the result cache, but I was pleasantly surprised to see that it is. Syscontext is now treated as effectively a bind variable inside a result cache definition. So as long as the bind variable value doesn't change, we can actually use the result cache as well. This is a nice little feature. I'm not sure when it came in, but it's something that has improved with result caching as time has gone on. If I change that result of that syscontext variable to 1,000, so now it's changed, the database is smart enough to see that this, even though it's a bind variable, has actually changed in value. So the first run will reprime the result cache, and the second one takes advantage of it. So it's pretty cool. Things like syscontext variables that are unchanging between executions can still take advantage of result cache, which is an improvement over its first implementation. I stress you do still need to take care here, and we'll wrap this up shortly about how I think we should always take care. Here's an example where UID is a user-delivered function from the database. UID is not a column on this table. UID is like sysdate. It's a function. The first execution primes a result cache. Will it be able to use it again? In fact, it actually can. So we're lucky here that even though UID is a internal function from the Oracle database, the database is smart enough to know that it's a constant. But how about if I do something different? How do I know that my user ID is 104? Well, normally I would query the database dictionary to do that. So here I'm making my query more functionally robust. I'm saying the UID is actually the user ID for me. I'm logged on as MCDONAC, Connor McDonald. I run that. I prime the result cache with the first execution. What happens on the second one? No result cache this time. This is unrelated to UID in this particular instance. It's actually related to the fact that I'm querying user users. Any query to a object owned by sys immediately disables result cache, even something as simple as user users. And we know that user ID is fixed for this session. So there are a list of rules. You can actually see this in the documentation for the result cache documentation, but it actually shows you that even though result caching has improved over time, you always need to take care as to which ones will be result cached, which ones won't be. Sysdate, systimestamp, anything with times in it, generally the most common culprits. And that's what I suspect is happening here for the person that asked this question, saying, why am I not getting result cache? So as we said, correctness trumps speed. The way I like always testing my result cache results is with autotrace, as we saw just in little demos there, or anything similar, whether using SQL Developer, SQL CL, or anything that can return you information from your session stats in terms of consistent and physical reads. You can look at the execution plan. The execution plan will generally always show you if a result cache identifier is a candidate for being used, but by no means is a guarantee it will be used. I probably should put these in the SQL Plus scripts. In the execution plan, you'll see, yes, I'm using result cache, and here's the result cache key, a pointer into the memory structure. But that simply reflects the fact that you had a result cache hint. It is by no means a guarantee saying that, yes, we will be able to use that result cache. So the execution plan, the explain plan, is simply not enough to guarantee it. You really want to look at the measurements, the output of the physical reads, to make sure you're getting that result cache benefit. And here's a little snippet from the documentation I mentioned before. There's actually more than this, but you can see generally bind variables, etc. are going to be okay. This is a restriction that's come out in later releases, but there are in 15.2.4.3 restrictions, temporary tables, sysschema, sequence values, SQL functions returning dates, etc. So while the documentation is there and it's always valuable, for me, the proof is in really testing it and actually seeing those physical reads drop with the result cache. That's how you really know you're getting the benefit. Rebuilding indexes. We currently rebuild our indexes every weekend as per the recommendation of our ops team. We're starting to worry about how long they are taking. How can I speed them up? There's actually a very easy way of speeding up your rebuilding the indexing, and we're going to talk about that today. So why do people rebuild? That's the first question I always ask, is why do people rebuild their indexes? And this is the most common response, is it told me to. Now, what is it when it comes to it told me to? Well, it's us, unfortunately. And when I say us, it's the internet. I went out and just had a quick search on the internet, literally this morning when preparing for this little topic here today. And this is what you find. Be aware, index spaces never reused. Next one, nothing you can do about it. You have to accept the fact that reorging indexes is part of your life. You should regularly build your indexes. Schedule a batch job to rebuild your indexes. Oracle server does not reuse index blocks to rebuild all the indexes. There's a ratio. If deleted rows is this. Oracle suggests dropping recode. Oracle index is not self-balancing. It keeps going on and on and on and on. All of this stuff is out there on internet land today, on blogs, in manuals, in books, everywhere. There's just this kind of thing. You just need to suck it up and say, well, that's just the price of doing business with the Oracle database. You need to rebuild the indexes from time to time. And the best thing is, all of that is total hogwash. And this is one of my favorite little slides. Don't believe you read on the internet just because there's a picture and a quote, some quotation marks around it. Most of those previous sentences are just fiction, or they have some very tiny layer of truth in them, but most of them are just fiction. So to prove to you how often you need to rebuild your indexes, I thought we'd go with a metaphor. Let's have a look. Hopefully you can all see this. This is a dictionary. As you can see, it's the Macquarie Budget Dictionary. But you can see, I spent $15 on you tonight, you attendees. I hope I get some respect here. $15 buying this at the local bookstore. This is just like an index. Why is it just like an index? An index in Oracle is entries stored in order. Unlike a table. A table's like this. In fact, here we go. I even have some ice. Right? When you put rows in a table, wherever they go, wherever they end up, doesn't matter. We don't care. It's called a heap table. But indexes are different. Indexes are things stored in order, and dictionaries are obviously stored in order. They start at A and they go down to Z or Z, depending on your accent. Everything is stored in order. A dictionary would be useless if it was not stored in order. So let's explore adding and deleting entries and seeing if we have to actually do anything in terms of rebuilding to preserve space in our index. Let me open up to a random page. Oh, look, it's only got 3 words on it. Oh, that wasn't that fortuitous that I landed on this page. The 3 words are common, complex, and compound. So there's the 3 entries in index order in the section that starts with words that start with C. Now, let's assume that I do something with this index, the table. I'm going to delete a row. I'm going to delete, oh, you can see I've got the blue tack there. I'm going to delete complex. Now, do I need to rebuild this page? It's now got an empty space in it. Well, not really. What if someone wants to put some data back in? Well, if they put complex back in, well, that's no problems, is it? It just goes straight back in. It costs me nothing to do that. But let's delete complex. What if I want to put the word compete in? That's different. But as luck would have it, compete fits in there as well. So as we take this back to an index structure, if I delete entries and put the same entry back in, no problems. If I delete entries and put different entries back in, but they still fit nicely in terms of index order, no problems. I didn't have to do anything with my dictionary. It works fine. Let's make it perhaps a little bit more realistic. What do we often do with data in tables? We delete the older stuff and insert new stuff. Well, that's a bit different, isn't it? Because now we're not sitting on the one page here. Now we're looking at stuff at the start of the index or the dictionary. So let's grab an early page. Oh, here we have. How fortuitous again. Only 3 entries on this page. We've got aardvark, abacus, and about. So once again, things at the very, very start of this index. So if this was timestamp information, this would be the oldest data. What do we often do? Well, we delete the old stuff. So, delete that one. Delete that one. Delete that one. Now it's totally empty. That's a problem, isn't it? Because I don't want to put any A's back in. I want to put in stuff that's new, stuff at the other end of this dictionary, stuff that starts with Z. I want to put zany in. But if I was looking after this dictionary, if I was a librarian or bookstore person, well, I've got an empty page now. I'm not going to leave it here. I'm just going to take it out and I'll just slot it in at the back. Oh, my C's fell out. I'll just slot it in the back where the Z's go. Because it was totally empty, I don't need to keep it up here anymore, do I? So maybe I can just whack zany in. And then when we add some new data, like zebra, that can go in there as well. And finally, zeal. I had a hard time thinking of Z words. Once again, the number of pages in my dictionary hasn't grown. There's nothing wrong there. So, from a dictionary metaphor, if I delete information, I can reuse the same slots with the C values. If I delete lots of information, I can actually reuse the pages elsewhere. You can't do that in a real book without tearing pages, but that's what I would do if I could with a index that is a dictionary. The question is a dictionary really like Oracle? Can Oracle do the same? Are Oracle indexes the same? Well, let's have a little play. Let's repeat some of those tests using real Oracle indexes. Now, because I promised I'd keep under the hour, we're going to do this quite quickly just with screenshots, not real demos. So I'm going to create a table here called T1. It's got 30,000 rows simply from 1 to 30,000. I'm going to delete all the multiples of 5. So I'm literally scattered throughout the entire table, deleting all the multiples of 5. So if this was our index, literally every 5th page is an entry roughly I'm deleting. you can see the size of the index is 66 blocks in size. That's the number of leaf blocks. There's a couple other branch blocks, but it's 66 blocks. If I put the same values back in, I deleted all the multiples of 5, put all the multiples of 5 back in, what happens? My index doesn't grow at all. It's just as it was before. Just like when I've lost my C's. When I deleted complex and put complex back in, right? No change to the index. Let's delete old data like the A's and insert new data like the Z's. So here's my table again, 30,000 rows from 1 to 30,000. I delete all the early rows from 1 to 5999, the first 6,000 rows roughly. The index is 66 blocks. I put brand new rows at the other end, at the Z end of my dictionary. So the rows used to go from 1 to 30,000. I'm inserting 30,001, another 6,000 rows. I deleted 6,000 down here and inserted 6,000 up here. And guess what? The index is still 66 blocks. It's unchanged. Let's now do different but fitting. This is the example where's my C row, where I took out compete and replaced it with complex. What happens if I have rows that would fit in order, but they're actually different values? So I'm going to create now a table which is all the multiples of 5, 30,000 of them. So still only 30,000 rows, but all the values are 5, 10, 15, 20, etc. I'm going to delete all the multiples of 30. The index is slightly bigger now because it's not 1 to 30,000, it's 5, 10, 15. Each number is a little bit bigger. It's one more block, 67 blocks. I deleted the multiples of 30, but what I'm putting back in is different values, 32, 62, 92. Still shifted by 30, but they're 2 out from the values I deleted. I deleted 30, I'm putting 32 back in. I deleted 60, I'm putting 62. So that's like this one where I'm putting a different value in, but it still should fit in index order, and guess what? The index doesn't grow either. So all of these scenarios show you that all these kind of operations, an index rebuild is simply not warranted because the index hasn't grown anyway. It's simply the same size. You get no value by rebuilding that index. Maybe this is the one. Let's go completely random. So here's my table again, values 1 to 30,000, 66 leaf blocks. And I've written some PL/SQL. I pick a random value between 1 and 30,000 and I delete it on line 6. Then I pick a different random value from 1 to 30,000 and I insert it. And I'm doing that 100,000 times, right? That's a lot of iterations, just over and over. So we started at 66 blocks. What do we end up with now? 82. The index has grown. This is like, that moment when Captain America holds the whatever it is sword that Thor owns, and Thor goes, I knew it. I knew there was a reason I needed to rebuild. Let's proceed. Let's keep going with that demo. So I've done 100,000 iterations. I ran another 100,000 and it went from 82 to 97. I ran another 100,000, it went from 97 to 110, then 119. The index continues to get bigger and bigger and bigger, and it's out of control. And so you might be thinking this is the worst case scenario, totally random deletes, totally random inserts, but maybe applications are like that. Customer deletes his record, some other customer inserts a record. Maybe we do need to rebuild. Let's keep going again. And don't forget, each one of these is 100,000 delete and insert pairs. It went from 129 to 131, and then 131 to, 131. In fact, it stayed at 131 no matter how many times I did those 100,000 deletes and inserts. We sort of reached this equilibrium point. And that's the thing. All indexes in Oracle have what I call like a steady state generally. They have a size at which they'll be happy, for lack of a better term. If I'm only ever deleting old data and inserting new data, then the odds are the index won't change at all in size. If I'm deleting data and inserting the same data back in, the index won't change. But even here, as you can see, if you're deleting and inserting completely random data, if the number of rows in the index isn't changing, it will ultimately sort of come to a steady state. And typically it's about 2/3 full. That's just the way B tree indexes actually work. They normally end up around about 65 to 70% utilized. In that way, they simply won't grow. But even so, you might be thinking, it was 70 or so leaf blocks, now it's 130, I need to rebuild it. So you rebuild it and it'll take it all the way down to 66. But if you have an application that is always doing 100,000 deletes and inserts of random data, guess what happens? As soon as you finish rebuilding it and normal activity resumes, it will simply grow back up to its equilibrium point. So what are you achieving here? You're simply saying, let's burn a lot of temporary space, let's burn a lot of redo, let's burn a lot of CPU and memory to shrink something down, and all it's going to do is grow to that same size again anyway. And while it's doing that, it's doing what we call leaf block splitting and branch block splitting. You're actually running your indexes slower and burning up more redo just to come exactly back to where you were before. Don't get me wrong, there are a couple of particular scenarios where you need to rebuild, but the vast majority of scenarios where you have indexes in Oracle, the rule of thumb is real simple. Do nothing. So for the initial topic of this, which was how do we speed up rebuilds? Really, really easily. You simply stop doing them. And then all you have to worry about is if you do see indexes that continue to grow in size and never reach an equilibrium point, they never hit that sort of 60% full and stay there, they're the ones you would then consider looking at remedial action. But you'll often find the number of indexes that need that in your database is commonly 0, and very rarely indeed. So key thing here is to speed up rebuilds of indexes, stop rebuilding your indexes, and you'll find things run a lot better anyway. Cool. 8:47, 13 minutes left, slow queries. We're going to get done. Slow queries in particular circumstance, and this circumstance is this. Each night we update all the rows in our customer table with the recalculated credit stores, but the next day queries seem really slow. They do get better during the day, but what is happening? It's all about blocks and what's in them. And we do a demo coming up now, but I was going to actually restart my database to do some changes, but we don't have to worry about that. I've already done it. So yeah, it's all about blocks and what's in them. Let's get some terminology covered off first. Most of the database consists of things that consume space, and we actually have a collective term for this. We don't refer to things that consume space in Oracle as tables, indexes, or clusters. We group them together and we call them segments. Anything that's a segment is something that consumes space in the database. Now, how do they consume space? Well, they consume it pretty simply. They must occupy space in files. That's what all things on a computer do. So those files are broken up into what we call extents. So as a table grows, you get given one extent. It's a chunk of storage inside a file. And so each extent consists of a file, because you can have multiple files in a database or table space. So we pick one, we grab an extent out of there. It has a starting position. It starts at a certain point in that file, and that extent has a length. So segments are made up of multiple extents, and those extents live in certain spots inside a data file, and inside those extents are the Oracle database blocks that make up your index or your table, etc. You can actually locate all this information yourself. This isn't all hidden from view. If you actually want to see where a table sits, you can actually go look at DBA segments, and there's two entries there called header file, header block. Also, there's a view called DBA extents, which actually has for every single extent for a given segment, what file it's in, the file ID, where that segment starts, the block ID, and how long it is in terms of blocks. So all that information is readily available to you, and we can actually see with a simple example that in real life. I create a table called T, I put one row in it, I can go look at DBA segments to find out the first block for that segment called T. It's in file 35, block number 9, and if I want to get really deep and dirty, I can actually dump that block out to a trace file. Or I can dump a range of blocks, but let's say I've dumped out just the first couple of blocks. It looks like this. Now, we're not going to spend a great deal of time on this because maybe another session we'll do data blocks dumps, but for this one, this is just a quick intro to how we can find information about a block. You can see there it's file 35, block number 9, and we have a thing called the block type. It's the data segment header. It actually doesn't contain data for your table. It's the first block that contains all the metadata about where I can start finding the extents, what kind of thing it is, etc. So it's like that your first pointer to where the rest of your table is. The second block is actually a type of trans data, transactional data. And we can actually see, if you sort of look down the screen here, it says it's a data block dump, and it has some information. And then finally, you can see right in the bottom, it has block row dump, and you have to start seeing things like the columns, etc. But the part in orange here is what we call the block header. Every block has some information at the start of it, which isn't the data in your table, it's information about the block itself. And this is actually in the concepts guide. You can actually see it says that every block consists of the common and variable header, the table directory, the row directory, free space, and then finally your stuff, your real data. But the key thing is every block has this thing, this common and variable header. And if we look at it, one of the things you'll see on that block header is a thing called the system change number. That is like the arrow of time, effectively the timestamp in numeric form of every single change that happens to the database. The first change, SCN number 1. The second change, SCN number 2, etc. for the life of the database. Every block has a system change number on it, which means every time I do a commit, every time I make a change to a row, which makes a change to a block, and commit, I need to update that SCN because I've changed the system change number. That's what it was originally. I commit, and there's a brand new system change number. What does that mean? It means every block has an SCN, and if you update every block and commit that transaction, then you need to update every SCN. Now that's a real nightmare because remember, we picked the SCN at commit time. So I've gone through this entire table and updated all the data I need to, millions and millions of rows. Then I do commit. Now I have to go back and update the SCN on all those blocks again. That is going to kill you in terms of performance. And when we see inside the Oracle database things that are going to be a real performance hassle for customers, what do? We do our best to avoid it. So we're lazy. Why would you go back and update all those blocks? Maybe we don't have to. Maybe we can just ignore it, and I'll come back to why we can ignore it shortly, but let's look at a demo first. So what I've done here is I've shrunk my database SGA down to a very small size. It's only 300 megs for the buffer cache. That means that most reads I do will come from disk, which is a good way of monitoring what's going on here. I'm going to create a table here which is 40 copies of DBA objects. That'll be, I don't know, somewhere in 8 million rows, somewhere around there. But it's a nice hefty table. I'm going to flush the buffer cache, so I'm going to see how long it takes to get all the information at worst case, all physical reads. There's 3.4 million rows in there, and it took 1.45 seconds to query this table top to bottom. If I run it again, it'll be a little bit faster. Oh no, it's about the same, right? Because it's all coming from disk. Now we're going to do this update where we change every single row in the table. Now I have to talk amongst yourselves, right? I think this takes about 20 to 25 seconds to do because it's 3.5 million rows. While this is going, I'll talk about how Oracle is lazy. As I said, we have to update every single row, and then we do a commit. Theoretically, we should go back and update every single block to put that SCN number in there. Now at Oracle, we're lazy. After you commit, we want to give you that instantaneous commit like we just saw on the screen there. So we're not going to go back and fix all that up. We're going to leave all those blocks that we've updated with correct data and what you could interpret as a corrupted SCN. The wrong SCN is in those blocks. We're not going to go back and fix it. That seems odd, doesn't it? But that's what we do because we want to get that commit to you super fast. Now that I've updated these 3 million rows, we're back on our demo, I'm looking at some particular stats here that have the word clean out in them. And the only real thing you need to worry about these ones is currently they're all near zero. Now, as I said, we did this huge update. It took a long time. The commit should have taken a long time, theoretically, if we're going to back and re-put all those SCNs in there, but we didn't. We simply said, let's not bother. Let's make that commit super snappy. Now, as I said, we've got all these incorrect SCN numbers that are littered throughout our table. Let's now run a query against that table. Remember the first one was 1.4 seconds? Now it's 2.7 seconds. If I look at my stats, notice now all these cleanout stats have bumped up a lot. What we do is this. We say the person who's updating, doing all this volume work, we're going to reward you at commit time by just leaving all those dodgy SCNs floating throughout the table. But someone has to pay the fiddler, so to speak. The very first person that queries those blocks, they'll read that block. They'll say, I want to get a consistent read. Here's an SCN number. That isn't the right SCN number for this block, because I can use that SCN, I can go hunt down some under information. It's either not there, which means it must be committed, or it's there and it says the transaction is committed, and yet this SCN says it's uncommitted. So the next person pays that price. Their job, even though they're only reading, is to fix up all the mess that the person that did the update's doing. We call it a delayed block cleanout. Someone else cleans up the mess. And you can see here that most of the stats here are about 67,000. We did 67,000 cleanups. Where's that number come from? Well, if we look at how many blocks are in that table, there's about 67,000. So the commit from the massive update was fast, and someone pays that price later, the next person to actually do a query. If I run the query again, now that they've done all that cleanup, you can see it's back to 1.5 seconds. So as you can see, one person has to pay that price because the person who did the update, they got the reward. They got the benefit of not having to do the cleanup. Now, why would we do that? Why, if someone has to pay that price anyway, why shouldn't we put it back on the person that actually is shouldering the burden, the person that actually did the update? Well, what we're doing is we're giving you the option. A real common thing that people do massive updates on is delete old data. And of course, what happens to data that's been deleted? Often people never want to query that data again. We do an archive a table and then we forget about it. The table is gone, or we do a huge update and we simply never touch that data again. So we're actually hoping to get lucky here. If you do a huge update on some data and no one ever touches it again, well then we gained here, we won. We never did that cleanup and we will never have to do it. That's what we call paying never. You get to choose. You might get lucky, but never have to pay that price. That's a good thing. The other thing you can do is, now that you know that delayed block cleanout is happening for the person that was doing these big updates overnight, is after you've done your update, you can be the person that then just runs a simple top to bottom query through your table. And that's what I call paying early. So if you know you're doing a huge update and you know that those rows will be visited by customers again anyway, after your large update, you should be the person that simply just runs a simple query top to bottom to do that cleanup, and then no one will ever know, or no one has to pay that price because you're taking on the responsibility yourself. But the reason we do this delayed block cleanout is because hopefully we might get lucky and never have to pay that price, and therefore everybody wins. We are done. Look at that, 8:59. I promised I would finish before the hour, and as I said, we have huge amounts of time left, plenty of time, at least 30 seconds left. Thank you very much for your time. As I said earlier on, if you're in Europe or Israel or Rome and Milan and you're at a conference, please come say hello. Say hello. I love talking tech. Thank you very much for joining. I hope you liked the new webinar format and you didn't have any problems. I actually had a few with my microphone. Hopefully you liked the little dictionary metaphor, and we'll see you next month for Office Hours. Thanks everyone for your time, and we'll see you all soon.